All right, so today we are going to talk about the single source shortest path problem. Okay. So we are going to use the Dijkstra's algorithm. Let's analyze that and see what is the opportunity for parallelism over there, right? So how does the Dijkstra's algorithm work, or what does it do, right? So you're given a source, and what you want to do is you want to compute the shortest path from this source node to all the other nodes in the graph, right? And when you run a single source shortest path algorithm, what you get is a tree, right? It's called the SSSP tree, single source shortest path tree, right? So A, B, C, D, E, F, G, H, right? So the output is a tree, right? And the path from S to any node in this basically is the shortest path, right? So obviously we are dealing with a weighted graph. Okay. All right. So how does the Dijkstra's algorithm work? Let's take a small example. Yeah. So let's say this is S, A, B. Okay, let's work with this example. So let's put some weights on this. So 2, and then 5, 3. Let me replace this with 1. All right. So this is the graph given to us. And now what we do is we again maintain something called the distance, right? The shortest distance for every vertex. So starting from S, A, B, C, D, right? And now what we do is, so initially what we do is we start with this. So we set its shortest path. So this is the tentative shortest path, right? Tentative shortest path means that so far, this is the shortest path that I have discovered in the algorithm. When the algorithm ends, then this D will actually be the shortest paths. Okay, the length of the shortest paths. And you can maintain the path with some backtracking, right? As you typically do in a dynamic program. Okay. So we're going to set this to 0 and all of these to infinity. And now what I'm going to do is I'm going to examine the cut, right? So this is the cut which separates, just like I did in the Prim's algorithm, right? I'm going to maintain a vertex set, okay, which is initially just going to have S, right? And now what do? Okay, I examine the two edges going out of S and I perform a relax operation on them. What is a relaxation operation? So a relaxation operation, so we'll define it. A relaxation on an edge, UV, relaxation on edge UV means that we check if D of V is less than equal to D of U plus the length or the weight on the edge UV, right? So if U is already in my set V, right? Then what I do is I just check if going from U to V, if I can get a shorter distance than what is already known for that destination V, right? That destination vertex V. And if so, then I update. Then D of V is equal to D of U plus WUV. Okay, that's the relaxation operation. So now what do? I basically look at every edge and I perform the relaxation operation. All right. What will happen once I perform the relaxation operation for S in this example? So I'm going to update the distances for A and B. So what is the new distance for A? The new distance for A is going to be, I'm going to replace this. Can I just replace it here instead of creating a new copy? And the distance for B is going to be 4. So that's going to get updated. And now what I do is similar to prims, right? I pick the minimum guy and I include him in my set V, right? So I include A in my set V. So this cut disappears off, and in my next iteration, what am I going to do? I'm going to examine the cut SA, all right? And again, I'm going to do the relaxation operations and so on, okay? Right, so what will happen now? Well, I have 4, 1, and 5. So what gets updated? Well, SB doesn't change. AB now, you realize that to B you have a distance of 3. You have a shortest distance of 3. So you're going to replace this with 3. So this will get replaced by 3. And C will get a distance of 7. All right, I shouldn't put a square right now around it. Okay. Now what happens? Now who has the shortest distance, right, from S in this graph now? So that is B. So B gets included in my set V, right? And now I examine the cut SAB, right? And so on. Okay. So you see the similarity with Prim's algorithm, right? It's almost the same as Prim's algorithm. So how do we design an algorithm for this? Simple. Let's go back to Prim's algorithm and let's do a copy paste. Okay. This was Prim's algorithm from last time. All right. I'm going to paste it here. All right, and I'll rename this to, so this is going to be my SSSP sequential. Now, what do I have to change over here? It's exactly the same. I recall what was there, right? So we had the set of vertices, the set of edges. We had weights associated with the edges. We had a root, right? And we wanted to start with the root. So root is my source S here, right? So initially I just put R in my tree. Again, we are building a tree in this case as well, right? It's quite similar. And I set dr to 0. And for all other vertices, I can just set their dv. And now what do I do? Well, I'm building a tree, so I know that I have to do exactly n-1 iterations. Yeah. Yeah, let me not worry about the parallelization parts right now. So what changes? Look, the difference is that earlier in Prim's algorithm, what was du? In Prim's algorithm, du was the shortest edge from t to v set minus t, right? And now du is what? Du is shortest path. Again, so far, right? This is tentative. Even the shortest edge was tentative. The shortest edge could be updated later in Prim's algorithm. Similarly, here the shortest path can also be updated. So I shouldn't say shortest edge, I should say tentative shortest edge, right? And this is also tentative. Tentative shortest path from S to S, or source here is R, right? Or R as the case may be, to U. So that's the difference. So D is not supposed to be the shortest edge across the cut, but it's supposed to be the shortest distance from S. So therefore, the only thing that will change is that over here, actually, this is going to correspond to a relaxation. And what's a relaxation? So relaxation, instead of this, I'm going to do the following operation. D of V is equal to min of D of V and D of U plus WUV. Right? That's the only difference. That's the only thing that changes. Okay? Nothing else changes. Is that clear? Any questions here? So I've just done a copy paste. So if you're confused about anything, please ask now. Right? So it's exactly the same as Prim's algorithm, except for the update operation is different, right? because you're not maintaining the tentative shortest edge across the cut, but you are maintaining the shortest path from length of the shortest path from the source to this vertex.